We're going to illustrate fully Bayesian inference for the number of components and the partition structure of a mixture model using the galaxies dataset that we had discussed before. As you remember, this dataset is available from the library mass in R, so we just need to load that library. We're going to need MCMC pack, as has been the case in the past, for generating from the Wishart distribution, which is one of my full conditionals. And I'm going to set the seed of the random number generator as I've done before, just so that you have reproducible results. So the code that we're going to use here, it's going to look in many aspects similar to the one we used during week 3 to fit Bayesian mixture models. There are going to be a couple of small differences. One is that the value of k that we're going to be using in this case is 30. And remember that because now we're going to do kind of this full Bayesian inference, the way in which you need to think about k is as the maximum number of components that we're allowing in the mixture. Which is typically, in terms of the actual number of components that gets used, is going to be smaller. And it's going to be controlled by the parameter that we use for the Dirichlet prior on the weights of the mixture. And so to decide what value to use for that parameter of the Dirichlet, we're going to solve a nonlinear equation, as we had discussed in a previous lecture. And in this case, we have 82 observations, so the Galaxy dataset has only 22 values. And recall that the information that we had about the number of regions in the space that had been looked at to collect this data was 6. So we expect, so it makes sense to expect that a priori we'll have about 6 components that are occupied out of the 30 that we are allowing for the model. So to find the value of alpha that we're going to use for the prior, what we need to solve is this nonlinear equation. And the way to do that in R is by using the uniroot function. So first we define the function that we want to solve, which is this one. And we want to find, so making the function equal to 6 is equivalent to getting the function, subtracting 6, and trying to find the 0 of that function. So we define this ff in this way, and once we have defined ff in this way, we use the uniroot function, and the uniroot function is going to take 2 arguments. The first argument is the function that we're trying to find the 0 for, and the other parameter that it takes is the range in which we're going to look. And typically, a range that goes between a really small value, you can't really use 0 in this case, but you can use a value that is really small, and something like 0.01 typically works well. And then you need a large value that defines the interval over which you're going to search, and something like 20 or 30 is typically a good value for this type of problems. So if you run this code, what you will see is that the root that R finds for this function is 1.49. I'm going to approximate that to 1.5. Just to keep things a little bit clearer. So the alpha that corresponds to 6 components in 82 observations is 1.5. So once we have done this little preliminary calculation that just reflects the prior knowledge that we have about the problem, then the rest is basically identical to the code that we had used before, except that now, rather than using a uniform for the Dirichlet, in the past this had been just 1 over kk for each one of the components. Now we're going to use alpha over k, and alpha in this case is this 1.5 that we obtained above. But otherwise, the algorithm is the same. So this just defines the hyperparameters for the model. This initializes the parameters. In this case, we're going to run a large number of iterations just to kind of be on the safe side. So we're going to do 25,000 iterations. And out of those 25,000, we're going to burn the first 5,000. So we're going to end up with only 20. The results are going to be stored in this matrices and vectors with all the samples. And then this is just the loop of the MCMC algorithm. Okay, so I'm going to run this. It's going to take a minute to run because, well, it's just a large number of iterations. So let's set it to run. And we'll come back in a minute once the algorithm has finished. Now that the algorithm has concluded, let's first do a plot of the posterior distribution on K star. And if you remember, K star is the number of actually occupied components in the mixture. And the way to do that is we're going to define our custom function nUnique that just count how many unique values there is in a vector. And we just apply that function to each one of the posterior samples of the configuration vector C. And then we just construct a bar plot for that. And what we can see after constructing this is that the posterior distribution, in this case, places probability anywhere between 5 and maybe 15 values. For the number of K star. The mode is clearly at 9. That is a little bit larger. Remember, our prior was centered at 6 or had an expectation of 6. Our prior here probably has a value somewhere in between 9 and 10. We can actually compute that very easily from the posterior sample. So the number is slightly above 9. And the mode is clearly 9. So the posterior distribution on K star kind of provides evidence for a number of components that is slightly larger than what we assumed in the prior in this case. The other thing that we can do, so this is not, K-star is not the only interesting summary of the posterior distribution. This only tells you how many components, in a sense, but it doesn't really tell you which galaxies go together in each one of the clusters. So if you remember from our discussion in some of the previous videos, the way to make inferences over that is by using a loss function, an expected loss function that then we're going to try to minimize. And the binder loss function that we discussed in the lecture depends on the pairwise probability matrix. So the next thing that we're going to do is construct that pairwise probability matrix. This little piece of code here does precisely that. And this just does a very big loop, one over the iterations and then over each one of the galaxies or each pair of galaxies, and just essentially counts how many times each pair of galaxies are assigned to the same cluster. And then once we have finished the count, we just divide essentially by the number of iterations in the sample. So that's what this piece of code will do for you. And once this finishes, we are going to plot the resulting matrix using a heat plot. And here I have a function that will do that. It's a little bit of a complicated function, but since this is something that you may want to do multiple times, it's useful to build a standard code that you can just call over and over again. And this is kind of a nice one because it will, in addition to displaying the heat map, it will display a color scale on the sides. So if you want to kind of delve a little bit into the details of how the plot works, you can look at this code in detail. But this function heat map plot, it's a self-defined function that is going to plot this pairwise matrix. And then once I have defined it, I just need to call it. And this is the kind of graph that you obtain. So what you have here is regions where there is a lot of red are regions where the pairs of observations have a high probability of being together. And you can clearly see here that there is a cluster of 7 observations that is very clearly all of them together. And then you have another small cluster here of 2 or 3 observations that are also clearly together and separate from everybody else. And the other extreme, you also have a small cluster here that is very well defined. Now, if you remember these 2 clusters in the middle that corresponded to those modes in the density estimate that some algorithms kind of try to put together, some of them try to separate, you can see that here the level of uncertainty in the clustering is much higher. So the left peak, there is quite a bit of certainty that the first observations belong together, kind of this square here. But then these additional observations, you have kind of more and more uncertainty about whether they belong here or they belong somewhere up here. And for this other cluster, there is a lot of uncertainty. So this could be a single big cluster, or it could be kind of a combination of 3, 4, or 5 small clusters. And it's the fact that you have so much uncertainty in essentially what is the configuration here, what is driving in the previous bar plot, what is driving the fact that your mode is coming up at 9, because there is many configurations in which this block here, it's split into 2 or 3 clusters. That's where the additional components are coming from in the mode. Now, this is good from the point of view of just giving you a sense of what the clustering structure is and what the uncertainty is, but this doesn't directly give you a point estimate. The point estimate is obtained by minimizing Binder's loss function. And here you're going to see a little example of code that allows you to minimize that function. So this LSTST is just the evaluation of Binder's loss function for one particular configuration. And then we're going to use an iterative algorithm to maximize that. So we just need to give it kind of some initial value. And the rest of the code just does an iterative algorithm that goes component-wise, maximizes Binder's loss function. So we're going to run that, and that actually runs pretty quickly in this case. And now we're going to redo this same heat map that we had constructed before. We're going to use the same function, but now we're going to add kind of vertical and horizontal bars that delimit what the point estimate is based on our Binder loss function. And in this case, we use, by the way, we use Binder's loss function with d bar equal to 0.5, which just means that the penalty that we impose for both types of errors, so clustering things together that should be separate and separating things that should be together, those two errors are given the same penalty, both of them. So that's why d bar is 0.5. So now if I create that other heat map, so this looks exactly like the previous one. It's just kind of adding this lines that corresponds to the point estimate. And you can see here what's happening. So clearly these two clusters that are very well separated, they are identified as clusters of their own. Same for this guy up here. And now it does, because of the level of uncertainty that is associated with the cluster, it is doing something a little bit different with kind of the things in the middle. So here it's linking together these two observations that are clearly together, have high probability of being together, but it's also putting together with those two this extra one that has this orange here that it's pretty dark. So it's more likely that this observation is with these guys than it's with any of these guys. So that's why it's putting it there. And then the other thing that it's doing is it's treating this big cluster here as a single unit. But here where you had a lot of uncertainty in the clustering structure, it's actually breaking it down into into 3 or 4 clusters. So it has actually a little cluster here that is a singleton. So this guy, because it could be either here or here, it's deciding to just put it on its own. Then you have these other two observations here that have relatively high probability of being together, but not clear that they belong to this cluster. And then the rest is being split into two components. So you end up with the optimal partition in this case under that loss function with the two errors being weighted equally, has 1, 2, 3, 4, 5, 6, 7, 8, 9. That actually corresponds to the mode of the posterior distribution of K star. In general, the two things don't need to match. And if I had used a different value for the bar, then I would have probably gotten a partition that had either more or less than 9. But in this particular case, it's nice that all the results match, and the value of K star that you obtain is the same as the number of clusters in the optimal partition that you get from Binder's loss function. The other thing that you can do with this is you can plot the density estimate that is generated here. And that's what this code will do for you. Again, it takes a minute to compute the density for all the MCMC iterations that we run. But what we're going to see is that the density estimate that we get in this case looks a lot like the density estimate that we had generated before when we had decided to fix k to 6 and just used a uniform distribution. So the model really is kind of quite robust, at least in terms of the density estimator, to the choice, as long as we kind of select this alpha value in a sensible way to reflect the prior information that we have.